Assalamualaikum and hi to all. So this is video part 6 of internal combustion engine part 2. So in this video, I'm going to explain diesel cycle. Diesel cycle. Introduction to diesel cycle. So in thermodynamic, diesel cycle is the compression ignition engine. It has also 2-stroke and 4-stroke types. So first we look into the diesel cycle's founder, which was first developed by Rudolf Christian Karl Diesel in the period of 1858 till 1913. And he is a German nationality, and occupation also as engineer. So the idea of diesel engines coming from the Carnot cycle of the fire piston. So this is the fire piston, which is a traditional fire starter using rapid adiabatic compression principles. So this system was developed and invented in Southeast Asia, particularly in the Malay Peninsula, Philippines, Borneo, Sumatra, and also Java. So first, we look into the diesel engine development. The first prototype was developed in 1893, and so this is the first prototype of the diesel engine. And in 1894, second diesel engine prototype was developed. This is the second prototype of it, and then the third and final diesel engine prototype. First fully functional diesel engine was developed in 1996. And in 1898, the first commercial diesel engine was developed. And this first fully functional diesel engine become the basic of modern compression ignition diesel engine. So this is one example of the diesel engine. And however, in the this system, we consider only a single cylinder, and by using the air standard assumption, to simplify the complex analysis. So the analysis become the ideal diesel cycle. Ideal diesel cycle compression ignition engine. So this is the PV diagram of the diesel engine. As you can see, we have an isentropic process, and we have two isentropic process, from process 1 to 2 and also process 3 to 4. And we have the top dead center and also bottom dead center, and then we have this constant pressure heat addition from process 2 to 3, and then we have constant volume heat rejection, process 4 to 1. So, and this is the TS diagram. We have, as I mentioned earlier, in the process 2 to 3 is constant pressure heat addition, and we have constant volume heat rejection from process 4 to 1, from the TS diagram. And this is the first process of the piston movement. So by using the air standard assumption, where the air circulated in a closed loop, it is considered a closed system, and certain process is well insulated, and it is in the quasi-equilibrium process. And first we look into the asymptotic compression, which is process 1 to 2, and then we goes to process B, which is the constant pressure heat addition, which is a process 2 to 3. We have Q in there, where heat is added into the system. And then we goes to the process C, which is asymptotic expansion, which is a process 3 to 4, where the piston move down and the volume is expand. And then it goes to the process D, which is the constant volume heat rejection. And here, as you can see, process 4 to 1 is the constant volume heat rejection. And the first process, which is a process A, is the compression stroke. And process B is the combustion. Process C is the expansion or power stroke. And then process D is the after expansion or before exhaust stroke, which is the 4-stroke system. And in all of the system, the valve, intake valve and also exhaust valve is closed. Now we look into the ideal diesel cycle analysis. First, we look into the FOR process, which is the asymptotic compression. It goes to the constant pressure heat addition, and then it goes to the asymptotic expansion, and it goes to the constant volume heat rejection, and it goes back to the asymptotic compression. So the process is in cycle, and we look into the PV diagram and also TS diagram. We have the top dead center, bottom dead center. We have two isentropic process and one constant pressure heat addition process and constant volume heat rejection process. And this is what I already explained in the previous slide. Now we look into the analysis. First, we look into the energy balance equation for the closed system. The same with the Otto cycle. We have Q in minus Q out plus work in minus work out, and it's equal to the internal energy of the final state minus the internal energy at the initial state. So first we look into the heat transfer process for process 2 to 3 and 4 to 1. And since it has pressure, we should include the pressure system. As you can see here, Q in is equal to P2 in the bracket times V3 minus V2 plus internal energy at state 2 minus internal energy at state 1. At state 3 minus internal energy at the state 2. And Q in is also equal to the enthalpy at state 3 minus enthalpy at state 2. And for the Q out is equal to internal energy at state 4 minus internal energy at state 1. And if you use the call air standard assumption, we can use the Q in equal to Cp T3 minus, which is the temperature at state 3 minus temperature at state 2. And for the Q out, we can use the Cv is equal to temperature at state 4 minus temperature at state 1. Now we look into the isentropic process, which is the process of 1 to 2 and 3 to 4. And here we first look into the volume ratio, which is a V1 divided by V2. It is equal to VR1 divided by VR2. And same goes to the VR4 divided by VR3. And it's equal to V4 divided by V3. As you can see in the Otto cycle, the value of V1 divided by V2 is equal to the value of V4 divided by V3. But in the diesel cycle, as you can see, we have a different volume ratio, as you can see in this equation, where V1 divided by 2 is not equal to V4 divided by V3. And by using the call air standard assumption, we have a slightly different value. T2 divided by T1, it is equal to the bracket V1 divided by V2 with the power of K minus 1. The same goes to the temperature at state 4 and state 3. And we can use the pressure. We can, how to say, replace the temperature with the pressure, as you can see in the equation as I shown in this slide. And it's also follow the gas law equation that state PV divided by T is equal to constant, and we can use this standard equation where PA times VA divided by TA is equal to PB times VB divided by TB, which is A and B is state 1, A is state 1 and B is state 2. That's for an example. And PV is equal to MRT. And the thermal efficiency of this system is calculated from this equation, where the thermal efficiency is equal to work net divided by Q in. And the thermal also can be calculated by using this equation, where the thermal efficiency is equal to 1 minus Q out divided by Q in. And for the cold air standard assumption, the thermal efficiency, we can calculate the thermal efficiency as the equation as I shown here. And the compression ratio and cutoff ratio. This is the compression ratio, which is the ratio of the top dead center or bottom dead center divided by the volume of the top dead center, and is equal to V1 divided by V2, and it's also equal to specific volume at state 1 divided by specific volume at state 2. And RC, which is the cutoff ratio, it is equal to V3 divided by V2, and it's equal to specific volume at V3 divided by V2. Okay, I already explained the diesel cycle and also the Otto cycle. Now we look into the differences between these two. First, we look into the diesel cycle. This is the four process of the diesel cycle. And now we look into the Otto cycle. And this is the four process of the Otto cycle. So now we look into the PV diagram of the diesel cycle. And this is the PV diagram of the Otto cycle. As you can see, the differences are at the process 2 to 3. Where we have in the diesel cycle we have constant pressure heat addition, whereas in the Otto cycle we have constant volume heat addition. And now we look into the equation that we use to calculate the Q in or the heat addition. For the diesel cycle we use the enthalpy at state 3 minus enthalpy at state 2, whereas for Otto cycle we use the internal energy at state 3 minus internal energy of the state 2. However, in the Q out, both of it use the same equation where it is equal to internal energy at state 4 minus internal energy at state 1. And since the process of diesel cycle of the heat in is constant pressure process, we use the Cp times the temperature at state 4, 3 minus temperature at state 2. Whereas in the Otto cycle, since it is a constant volume process, we use the Cv times temperature at state 3 minus temperature at state 2. For the Q out, both of the system use the same equation, and since both of it is a constant volume process, we use Cv times the temperature at state 4 minus temperature at state 1. And for DC cycle, we have a cutoff ratio, which is RC, and it is equal to V3 divided by V2, or it is equal to specific volume at state 3 divided by specific volume at state 2. And for the Otto cycle, we have the ratio of the volume, and it is equal to volume at the bottom dead center divided by volume at the top dead center, and it is equal to V1 divided by V2, and it also equal to specific volume at state 1 divided by specific volume at state 2. Revision question for Otto cycle and diesel cycle. Try to look into all this equation, and hopefully it will help with your study and also your revision. This is the end of part 6 for chapter 2. Hopefully you enjoyed this video and it is helpful with your study, and thank you.